Imagine managing a fleet of delivery trucks where the fuel prices change every minute. You have a fixed budget for fuel, but you also need to deliver packages quickly. If you stick to one truck because it was cheap yesterday, you might run out of money when prices spike today. This is exactly the problem facing systems that serve large language models. We are dealing with environments that are non-stationary, meaning the conditions change constantly. Prices for different models fluctuate. The quality of responses might drift. User preferences shift. A static routing strategy, one that picks the best model based on old data, simply cannot handle this volatility. Enter ParetoBandit. This is an open-source adaptive router designed specifically for this chaos. It combines cost-aware contextual bandits with a unique budget pacing mechanism. The core innovation lies in how it balances quality against cost in real time. To understand how this works, imagine a thermostat. A standard thermostat turns the heat on or off to maintain a temperature. ParetoBandit is like a smart thermostat for your budget. It does not just look at the current price of a model. It looks at the cumulative spending against a dollar-denominated ceiling. It enforces strict limits without sacrificing the performance you need. Here's the thing about traditional budgeting. Most systems try to optimize for cost or quality independently. ParetoBandit optimizes for both simultaneously. It uses a primal-dual budget pacer. This is a mathematical framework that adjusts the routing policy dynamically. If you are spending too fast, it slows down. If you have budget left, it explores more expensive models that might offer better quality. This ensures costs never exceed targets by more than a tiny fraction. In testing, the system kept spending within 0.4% of the target limit. Now consider how it adapts to change. The environment is non-stationary. A model that was cheap last month might be expensive today. A model that was great last week might degrade. ParetoBandit uses geometric forgetting. This means it trusts recent data more than old data. It is like a student who studies for a test tomorrow more intensely than for a test last year. When a price shock happens, the system forgets the old pricing structure quickly and learns the new reality. This allows it to detect silent regressions within budget. You do not lose money while the quality drops. Another mechanism is the hot swap registry. This allows new models to be onboarded at runtime. Imagine adding a new truck to your fleet without stopping the delivery service. The system can introduce a new model and reach meaningful adoption in approximately 142 steps. This is incredibly fast for a system that must also respect budget constraints. It does not breach limits while learning. The decision latency is under 23 microseconds. This means the router adds almost no delay to your actual requests. There is another approach called Pilot. It aligns query and model embeddings in a shared space. It treats cost as a multi-choice knapsack problem. While this is a valid method, ParetoBandit focuses on the specific challenges of extreme non-stationary environments. The geometric forgetting and primal-dual pacer work together to handle sudden shifts better than embedding-based alignment alone. The consensus across these studies is that online, budget-constrained adaptation is necessary. Static, offline training is not enough for the real world. Evaluations across 1,824 prompts demonstrate the efficacy of this approach. The system achieves a quality lift of 0.071 following significant price changes. This means when costs go up, the router finds a way to maintain or improve the user experience without breaking the bank. It learns optimal routing strategies from bandit feedback. This is reinforcement learning applied to routing. It enables a single policy to navigate complex trade-offs between latency, cost, and accuracy. Think about the future of LLM serving infrastructure. It will likely evolve towards autonomous, self-adjusting routers. These systems will continuously optimize resource allocation based on real-time feedback. They will not rely on predefined rules that become obsolete the moment market conditions change. This represents a fundamental shift in how we manage computational resources. We move from managing servers to managing workloads. We move from static rules to dynamic policies. The integration of reinforcement learning with budget pacing allows for significant cost reductions compared to baseline routing strategies. You get better quality while paying less. This is the promise of adaptive routing. It ensures long-term LLM serving stability. It handles shifting user preferences and model performance degradation over time. It offers a robust solution for the instability that defines modern AI infrastructure. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.